Uh, so now it is my great pleasure to welcome today's speaker, Professor Shaowu Pan. He is an assistant professor in the Department of Mechanical, Aerospace, and Nuclear Engineering at Rensselaer Polytechnic Institute, and he's also affiliated with the Rensselaer IBM AI Research Collaboration. He received his master's and PhD in aerospace engineering and scientific computing from the University of Michigan in 2021. He then spent a year as a postdoctoral scholar in the AI Institute of Dynamic Systems at the University of Washington. His research interests lie in the intersection between computational fluid dynamics, data-driven modeling of complex systems, scientific machine learning, and dynamical systems. So it's a great pleasure to have you today, and Shaowu, the screen is yours.
Awesome. Thank you, Savis, for the warm introduction. Hi, everyone. Today, I'm going to talk about a Neural Implicit Flow, my postdoc work at UW. It's a mesh-agnostic representation learning paradigm for parametric spatial-temporal field. Okay, so first, I want to give a little bit, why it's frozen? Okay, great. A little bit introduction, kind of a background introduction to this problem. So I know most of you probably are in control community. So I want to kind of find an overlap between fluids and control. So if you draw a Venn diagram, all the overlap is basically from a dynamic system perspective. So if we think about fluid system as a dynamic system, so basically think about PDE system as a dynamic system, the easiest way to think about it is basically discretizing this PDE, and we end up with giant ordinary differential equations. And if we think about this perspective, the fluid system contains a really huge number of spatial degrees of freedom. So that's basically, that's the key thing that distinguishes fluid system away from typical nonlinear dynamic systems. However, many practical tools and theories in the modeling and control community are designed for low-dimensional systems, which means not low-dimensional, not necessarily, that's kind of low compared to the fluid system. But however, is fluids necessarily infinite dimensional? Is it because if you talk to, I remember I have experience talking to control people during my PhD, and she said fluids are really complicated because it's infinite dimensional, and how you're going to deal with that. And probably, but however, fluids not necessarily infinite dimensional. If it is really infinite dimensional, then probably if you think about, let's say, think about the value of a pixel in fluids, and it seems like if it's really infinite dimensional, that means any kind of arbitrary values at this pixel combined with all the other pixels with all the kind of combinatorial large number of combinations would be a valid solution, the valid solution for the sort of valid or physical state of the system. I don't think so. Okay, so fluids are usually contains, as you can see, for example, on the left figure over there, you can see this fluids has, this is probably a ISO control of a Q criterion or viscosity magnitude. But as you can see, there are some, looks like there's some kind of structures with some patterns, although the pattern is a little bit complex or a little bit chaotic, but there's some pattern over there. And this pattern happens over and over again, no matter if it's a bird, or if it's a cat, or if it's whatever object in the air, if it's moved around, it seems to have sort of similar patterns. So fluids are not necessarily infinite dimensional. But however, the nominal dimension can be really high based on the mesh size, based on how you discretize the system. So the goal here is that, well, if we want to leverage the modeling, if we want to leverage the tools that develop in modeling and control community, the first thing we got to do is we need to reduce the spatial degrees of freedom. Even from a learning perspective, it's also beneficial to reduce the feature space into a low-dimensional space where interpolation can happen using a much lower sample complexity. Okay, so this field basically point as dimensionality reduction. So the state of art in this field, I would say from the fluid dynamic perspective, is basically two kind of methods. The first one is so-called proper orthogonal decomposition. So basically it's a statistical tool originally in the statistics community, but is brought to the fluid mechanics in a methodology conference in 1965 by John Lumley. And after that, the fluids community basically just call, well, the actual SVD as POD. So the algorithm behind POD is called basically the singular value decomposition. It's a matrix decomposition techniques. So basically, it's trying to find a low rank decomposition of a arbitrary matrix. Okay, so this is how it works. So in fluids, so how it works in fluids, basically you think about you have a bunch of images. You think about fluids as for now as a bunch of images over there on the left, and you can if you have an index for all the nodes in this meshes, you can actually flatten them into 1D array, right? You have the first one corresponding to the first element, and the last one corresponds to the last element values over there. Let's say let's say, for example, just temperature. Okay, and then you can, for each, the flow state can be represented as a really long vector. Let's say just each vector contains all the temperature information at each point. Okay, and then you can stack them. You can sort of stack for each time step. You can stack this long vector horizontally into a big matrix. Perhaps it's going to be a tall, skinny matrix if you have really a large number of cell elements. Okay, and then for that matrix, you want to do a singular value decomposition, basically trying to extract the USV transpose corresponding to that big matrix, and the V transpose over there, basically the one you see on the right arm, the third one on the right hand side, and that's contains the same number of columns as the previous original matrix, but it has a much smaller number of rows compared to the original matrix. Remember that the number of rows in the original matrix corresponds to the number of cells in the flow field, okay, in the discretized flow field. Okay, so if you are able to, and actually as you can see, this fat V transpose matrix over there, this short fat V transpose matrix over there is actually this is actually what we usually call the latent representation, because it can be this from the big original matrix to the V transpose matrix. This process can be thought as a dimensionality reduction in the spatial directions. Okay. And second, there's I would say in the recent, probably it's probably starting from 2015. There's a tendency using convolutional neural network instead of this POD, because POD has many issues. Proper orthogonal decomposition would have really a tough time to deal with solutions this direction dominated. A very simple example, a thought of experiment, it basically goes like this. So imagine you have what kind of matrix you think it's impossible to have low rank decomposition, and what kind of physics phenomena you would correspond to. Think about a triangle wave moving from left to right. Okay, your computational domain is 1D, a triangle wave moving from left to right. You know this is nothing but a triangle wave moving from left to right, and it's the simplest thing you can think about in fluid dynamics. And this corresponds to, if you stack these, if you create a data matrix by stacking them horizontally, you will find that this matrix is a diagonal matrix. And a diagonal matrix, unfortunately, it basically, you can't really have a meaning for a low rank decomposition, right? So for active action dominated problems, a POD would, you really need to use maybe hundreds of modes to actually, not just tens, but hundreds of modes and thousands of modes to accurately represent a flow field if the active action dominated. Okay, so this is basically triggers. That's basically the motivation for using kind of a nonlinear methods instead of linear methods to find a latent subspace. And because of the popular, growing trend of deep learning, and people start to think about how about let's downplay fluid dynamics as images, just pure images, pixelized images. Okay. So then, if you're willing to pay the price, you can actually just leverage the convolutional autoencoder as a way to find the latent representations for this flow field. So basically, what happens is first you perform some uniform pixelizations, as you can see from the bottom left of the slide, and then you perform some pooling and convolution process, and you can perform again, and then in the middle you kind of flatten them into a little bit long pencil, and then you can use a simple feed-forward neural network, a bottleneck sort of autoencoder type of framework, simple neural network, and create a latent representation, and then you perform the transpose the convolution again to kind of map back to the origin of sort of the image space. Okay, so that's the state of the art for dimensionality reduction. Okay, however, pay attention to the risk graph. That's basically where that's basically the assumption of those two methods, and that assumption causes them big troubles in applying to realistic, data set, especially in the world of CFD. Okay, so the data structure in the real world of CFD is actually much more complicated than this. So this is an image from a Boeing. So as you can see, this is a CFD simulation for an entire aircraft. As you can see, those meshes over there, you can guess that this mesh is actually an adaptive mesh based on the vorticities, probably based on the vorticity over there. So we know when I recall your aerodynamics class, one of the most important characteristics in modern aircraft is a wingtip vortex. Okay, the wingtip vortex over there basically is just the difference between the upper and lower wings, and it basically causes the air from the bottom moving to the up, and basically cause the byproduct is basically called a vortex, a pair of vortexes. And the pair of vortex over there requires smaller meshes size to resolve, to accurately resolve the vortex. So in the real world of CFD, adaptive mesh refinement would be a really smart strategy to accurately solve the flow field, but not really refine the mesh where is needed. Okay. However, if you look at this picture over there, you can see if the mesh, because the mesh is adapted over time, that means the mesh topology is changing over time. If the mesh topology is changing over time, first, there may be cells, previously maybe in this region there's 10 cells, but in the next second it could be 20 cells or maybe 40 cells. Okay. So in overall, the number of cells can change over time. That's the first thing. And the second thing is, remember that previously when we're using the SVD, we're assuming we have the number of cells, each number of cells has the index over there, and that index does not change over time. But however, in this case, when we have these adaptive meshes, how are you going to sort of naming the, how are you going to do sort of given that order for those new cells? Are you going to put them in the very end? Or you want to put them somewhere in the near where it's generated, near those previous cells where it's generated? It seems like it's probably something, if you consider things from HPC perspective, you might want to come up with different strategies based on the hardware. So this just if you're trying to pursue that, there will be a rabbit hole. It's gonna never end. Okay, this is problematic. Okay, therefore you cannot really apply singular value decomposition for those meshes and for CFD simulations that lies on adaptive meshes. Okay, the second example is basically when the meshes changes with different parameters. Okay, so when we do CFD, the reason why we're doing CFD is because we wanted to form digital simulations about the realistic physical objects. And when we do that, of course, we wanted to change the operating conditions to see what happened, to answer what-if questions. Okay, so for some problems, let's say this is supersonic inlet, and you would have, when you're changing the pressure ratios, you will find that the shock locations will change. Okay, the shock location corresponds to a strong discontinuity in the flow field. Okay, and typically a good CFD engineer will refine the mesh near the shock. Okay, trying to reduce the numerical error resulting from it. Okay, so that means if you have different parameters, okay, and the mesh will be different, and the mesh will be different. Therefore, you don't really have, if you wanted to, if your goal is to come up with a surrogate model that's kind of able to predict what's going to happen, what if the operating condition is somewhere in between, for unseen operating conditions, you cannot really use singular value decompositions for reducing dimensionality of the flow field, because for different parameters, for different training data, it has different mesh size. Okay, it has different mesh topology. Okay. Previously, I just talked about the downside of singular value decomposition, but how about convolutional neural network? Okay, so convolutional neural network, unfortunately, it's not gonna work in both of those cases as well, because you would need a uniform pixelization. So as you can imagine, if you're using uniform pixelization, if you really want to have, let's say, a guaranteed small error, you will probably need to use a really, really huge number of cells to capture every single details. And in some areas, those pixelization is totally a waste of resources. And that actually leads to a very important conclusions. I would say actually is the conclusion is from computer graphics community. Okay, they're also trying to use convolutional network to solve to process 3D data, but they find that actually you can go on to read the paper, and if you choose to use convolutional neural network structures or architectures for processing 3D data on sort of the modern medium to high-end GPUs, let's say you have 24 gigabyte on a single GPU card, you can't really go beyond 64 cubic. If you're using, let's say, a standard UNet, you can't really go beyond, and using a reasonable amount of batch size, you can't really go beyond 64 cubic. These resolutions, 64 cubic, the resolution is actually is a state of art in the world of CFD 60 years ago. Okay, so of course right now it's very easy to go beyond millions of cells, especially in 3D. If you go to the world of 3D, so convolutional so basically there's absolutely no way you can use convolutional autoencoder framework for 3D realistic CFD simulations. Okay, so just to conclude, POD and CNN cannot really handle parametric varying mesh topology, adaptive meshing, or problem with multi-scale, multi-resolutions, because there will be a waste of time, or you basically can't really, it will be a waste of time if you use convolutional autoencoder. And if you want, and because of the memory actually goes in the CNN structure, it goes cubic in 3D cases. There's no way you can have a scalable 3D nonlinear dimensionality reductions based on these two technologies. Okay, so we need a new solution. So basically, a new solution that I came up with is called the Neural Implicit Flow, which I believe is a third generation paradigm for dimensionality reduction in the world of CFD. Okay. So here is basically my framework. This framework contains of basically two neural network. The first one is called the ShapeNet, and the second one is called the parameter. The ShapeNet takes the XYZ spatial coordinate as input, and the ShapeNet inside the ShapeNet, it could be just a simple feed-forward, a multi-layer, feed-forward neural network. But the thing here is the weight and bias of the ShapeNet of that multi-layer feed-forward neural network is actually an output of another network, which is called a ParameterNet. And the ParameterNet takes any other factors. It could be time, it could be parameter Reynolds number, Mach number, it could be some sensor, some sensor values. Let's say you have 100 sensors for temperatures on the wall, and you know there's a relation between the temperature distribution on the wall to something other quantity. Then you can use this framework, and you feed the information of the sensor into the parameter. Okay, and basically between the ParameterNet and the ShapeNet, you can create a bottleneck type of feed-forward neural network, and the narrowest layer over there, the numbers over there, the values over there corresponds to the latent representation. Okay, and of course the final output of the ShapeNet corresponds to the quantity of correspond to your quantity of interests. Okay, so this is basically the architecture of Neural Implicit Flow. It's very straightforward, as you can see, and these architecture and also has a special name called a hypernetwork in the computer science community. Okay, and now since we have understand how this architecture works, we can actually think about a problem. Let's say on the left, as you can see on the figure, you see this is actually a famous Rayleigh-Taylor instability. Okay, so basically it's a flow simulation. Basically corresponds to if you have a heavier fluids and you have lighter fluids in below, but heavier fluids on top of the light fluids. As you can see, the light fluids, of course, if there's a disturbance in the interface between the heavy and light fluids, and that disturbance actually will grow. And this is called, it will grow sort of the mushroom type of structure. I think if you pour milk into coffee, you will probably have some of the phenomena like this. Okay, so as you can see, these mushrooms, they basically grows near the interface. So a smart way to simulate this kind of problem you would need to. Someone have a question, Hassan? Yes. What is your question?
Hi, Shaowu. I'm just curious about this the structure that you show over here. So the latent representation is that an input to the ShapeNet, or is it being like, or is it a temporary, like a partial output from the ShapeNet before it goes to you?
It's a very good question. It's you can think about it's an input to the ShapeNet, but the way it goes to the input of ShapeNet does not go like a normal neural network takes in. Okay, a normal neural network, when it takes input, it goes to the first layer. But the latent representation, when it is if you treat it as an input to ShapeNet, it does not go to the first layer. It goes to every single layer of ShapeNet, because every single layer, every single weights and bias in every single layer of the ShapeNet is controlled by the latent representation.
I see. So effectively, you have a secondary input, and then it's being mapped to some latent space, and then that latent space is being passed on to every layer in the ShapeNet.
Correct.
Okay. Okay, and all right, yeah. I mean, I can see the difference between that and just stacking the external factors to the input.
Yes, actually, I have a comparison to that. I have a comparison about, does that bring me any benefits? I will show you in the next slide.
Okay. So just to follow up on this question, what is the mapping from the latent representation to the parameters of the ShapeNet?
Yes, the mapping is it's a great question. It's a simple linear mapping. Just a linear. You have a big linear matrix mapping from 3 to maybe 10,000.
Okay. And are the weights of that mapping itself trainable?
The weights of the mapping, this linear layer is trainable.
Yeah.
And that's basically 90% of the trainable weights are over there. Hmm. It's a very good question. Okay. Another question I see. Yes.
So I had one quick question. So I think it's interesting the line of work that you're presenting, but like as you drift away from the original SVD formulation, you're kind of losing the structure in the latent space, right? That SVD kind of gave you orthogonality, for example. Now I don't think you can impose such structure. Like, do you think that has an impact on whatever, like your downstream tasks?
Sir Moitroya, we cannot hear you very well. You're far away. Could you please repeat that?
Mm-hmm.
So I was wondering if I mean, as you move away from the SVD formulation,
yes,
you kind of sacrifice the structure of the latent space, right? Like there is no orthogonality, for example. So
yes,
that has any bearing on the
that's a great question. So first, ask yourself why do you need this latent representation? If you really want the spatial-temporal field to be decomposed linearly, then you need that. You need this kind of orthogonality. You need this kind of linearity. Yes, you do. But if you just need this latent representation in order to make predictions, you don't actually care. You don't care about that. If you want to use latent representation for predictions or controls, you don't really need that.
Right.
Yeah.
Sure.
And in order to satisfy you a little bit more, I actually create there's actually a special treatment for this framework that it can be especially for you if you really like this linear representation, like this kind of well explained structures. I have a framework that basically only parameterizes the last layer, and it is achieved, as far as I know, the first time that is the dynamic mode decomposition performed on adaptive mesh. I'll show you in 5 minutes.
Thanks.
Okay. Yes, they are great questions. Okay, so
so we actually have one more. So we have one more question from Terry.
Yes.
Hi. I'm a little bit just follow Hassan's question. So the latent representation, my understanding is the ParameterNet is trying to pull the latent representation kind of independent of these external factors, or try to be invariant to the input.
Let me see. So the external factors will go to the ParameterNet. ParameterNet takes external factor as input, and it outputs the latent representation. So the latent representation is determined by the external factors.
But at the same time, the latent representation is also kind of like dependent on the ShapeNet, right?
No, it's not. It does not determine. The latent representation will determine everything inside ShapeNet. So the information, that's the sort of. I know my graph doesn't really show how the information on dependency flows, but basically it goes like this. So external factors, information goes from external factor, goes to ParameterNet, goes to latent representation, and goes to the weights and bias of the ShapeNet. And that will collaborate with the spatial coordinates to give you the quantity of interest at that point and at that external factors, given that external factors.
All right. Okay.
Great. Good questions. Okay. So as you can see, in this framework is, if you want to train this framework, basically all you need to do is sort of the point-wise samples. It's similar to DeepNet. Basically, you would need each data point is basically contains the spatial coordinates and the external factors and corresponding the quantity of interest. Okay, so as you can imagine, for 3D problems, even for 2D problems, the number of data can populate really, really large. It can easily goes to 1 million data points. But the good thing is, the bad thing is, of course, is because it's sort of the point-wise sampling, you seems to have a really huge number of data. But the good thing about it is it's very flexible. Once it's trained, it's very flexible. You don't really need some sort of well-organized mesh topology. It can be any mesh. The mesh can change over time. It doesn't matter. It works as well. Okay. And once it's trained, it can evaluate at arbitrary locations, which is also, let's say you are trained this framework on 128 square. You can evaluate on 512 square. Okay, great. So to summarize, it enables a mesh-agnostic representation of spatial-temporal fields. And a nice thing about it is that the model complexity only scale, as actually this is the underlying reason why it works so well, is the model complexity only scale with the complexity of the signal itself rather than being affected by meshes. If you think about SVD or CNN, they are all affected by the meshes, the complexity of the model, the computational complexity of the model. Okay, but here it's never the problem because we basically optimize the thing we really care about is just the neural network weights. Another example, for you to easily understand, think about a straight line. A straight line, I can put 1 million points on a straight line, right? But a straight line is only 2 parameters, right? The slope and the intercept, right? So if you think about this in a neural network sense, these neural implicit flow do make sense. Right. Okay. I think I just described the framework, and now I'm gonna, give you some a little bit. Just this is probably the one last slide about the architecture argument sort of thing. So the NIF can be viewed as a nonlinear generalization of DeepNet. So DeepNet is a very famous work. I think it's first published online on arXiv on 2019 October from Georgia Karnidakis group. At Brown University. So the DeepNet basically contains sort of the 2 networks. One is trunk net, the other is called a branch net. Okay, so the neural implicit flow, if you look at this, the figure, neural implicit flow versus DeepNet, if you look at it carefully, you will see that actually the neural implicit flow, the DeepNet can be interpreted in neural implicit flow by just saying that the ParameterNet only parameterize the last layer of ShapeNet. Then it becomes very similar to DeepNet. And that also gives you an insight about DeepNet. The DeepNet is essentially a linear structure. Therefore, this is how I call NIF is a nonlinear generalization of DeepNet. Okay. The figure 3 is a neural operator. It's a different thing, but if you are curious, maybe they have shared some names together, but it's totally different thing. Neural operator is based on a graph neural operator, so it still suffers from the issue of they still suffer from the issue of the model complexity scale with the meshes. Okay, that's why neural operator can really scale to 128 qubit problems. You have to play around with some HPC tricks to do that. Okay. Okay, so here's a sort of kind of solid evidence. If I compare DeepNet and Neural Implicit Flow shoulder to shoulder, I'm comparing it. So think about a 1D traveling wave problems.
Sorry, before you go into that, Hassan has a question.
Oh, Hassan has a question? Yes. I love to hear questions.
Can you back up one more time to the comparison between the architectures?
Yes.
So it's still not clear, I guess, or I guess you haven't shown us how the latent representation variables are actually passed onto the ShapeNet architecture. Could you tell us a little bit about that?
Yes, I can definitely talk a little bit more about that. Unfortunately, I don't have a good slide to illustrate that, but I'll try the best I can. Okay, so from the latent representation to the ShapeNet, let's assume the ShapeNet contains 5 layers, and maybe 5 layers has 300, in total 300 weights and 300 weights and bias. Okay, now let's say the latent representation is only 3 dimensions, basically 3 golf balls that you see over there. Now there's a mapping from 3 to 300. That 3 from 300 is a linear mapping. It's a matrix with size 3 by 300. That matrix is trainable. You want to tune that matrix. Okay, so once you have the values for the 3 golf balls, you can multiply that matrix, basically give you a vector of 300 by 1, right? That 300 by 1 vector will be distributed, will be partitioned into the corresponding layers, into corresponding locations in the ShapeNet. Maybe it's the first layer, weights and bias, second layer, weights and bias, and goes to the 5th layer, weights and bias. And basically, once the golf, that's easy to say, once these golf ball values is determined, the weights and bias in the ShapeNet is determined. And then, given the spatial coordinates, you can evaluate the output field given the weights and bias determined by the golf ball in the ShapeNet. Does that make, is it better?
I think so. So if I may reiterate, then
yes.
Then the ShapeNet itself does not have parameters that are being computed in them.
Yes.
What you have is a network that's mapping from the latent representation to what the weights and biases of the ShapeNet should be.
Yes, that's correct. The ShapeNet is a clown. It's controlled by the strings on his hands. It's controlled, by the string on his hands, which is connected to the golf ball, which is further determined by the parameter.
Okay, and so you would have, like, for however many layers you have in ShapeNet, you would have as many matrices that are mapping from the latent representation to each layer in the ShapeNet. Is that also correct?
Yes, although I will chunk them into a big matrix.
Sure. Okay. Yeah. Okay, I see. All right. Thank you.
No problem.
For this step, why wouldn't you use a nonlinear map from a latent representation to weights of the ShapeNet?
Why not using a nonlinear mapping, right? Why using a linear map? Is that the question?
Yes. Yeah.
Yes. So that's a great question. So if I use, it's more from the perspective of computationally, I want to make the computational affordable. Okay, if I use a nonlinear mapping, then that means, let's say I'm using I would say a 2-layer. If I use 2-layer, it can be a little bit problematic. So if I use 2-layer, it will significantly, let's say I have 3 mapping periods. I'm mapping from 3 to 300. If I'm using 2 layers, maybe 3 from 3 to 10, and 10 to 300. Then the 10 to 300 will basically cause a little bit a lot more memories in my GPUs. And another thing is I also tried to, even for a single layer, I tried to have some activation on it. basically a single layer, single matrix modification, then followed by element-wise activation, either using tangent edge or using other ELU or ReLU or maybe other switch activation functions. It does not give me much benefits. So that's why I didn't use the sort of the from the latent representation go to ShapeNet. I just use a simple linear network.
Thank you.
Yeah.
So,
looks like we have another question.
Yeah.
Yeah. Hi. So I'm really confused at this point. You said the ParameterNet, and no, you said the ShapeNet is static. You're not learning anything.
Yes, I'm learning it.
And how does this scale if you change the boundary conditions or the initial conditions? So you only have the ParameterNet that is changing, which is function of time and some physical parameters, I assume.
Yes.
So if you change the boundary conditions, is the model still valid, or how do you?
That's a great question. So I can put the information of the boundary condition into ParameterNet as well.
Into the parameters.
Yes. For example, the sensor values. You can put sensor values into a ParameterNet. The sensor value could be corresponds to the maybe five uniformly equally spaced locations on the boundary, and maybe you get these temperature values at those 5 points. Maybe it's a good approximation of the temperature profile on the boundary, and you can put that into a parameter.
And if you change completely the boundary condition, do you still have valid solutions?
It's a great question. It depends on the nature of the problem. If you're trying to use this temperature to predict the chaotic turbulent velocity away from the wall, I will run away from this. It's probably not going to work at all. But if these 5 temperatures is going to predict, let's say, maybe the mean temperature profile, time average temperature profile near to the wall, maybe just 10 cells above, then I would probably say maybe it's a good shot.
So not too far from the trained boundary conditions. The thing that is shocking me, I thought I understood, and then your answer to Hassan threw me off, because if you're saying it generalized with respect to meshes, then I was expecting the ShapeNet to take over that generalization. But if it's static, it's rigid, if you change the boundary condition, and you would need in a classical solver a completely different mesh, I don't see how this can adapt to that.
Yes. So
it's not changing. So
right. Let me see. So if the boundary condition, if I'm not sure if I understand your question correctly, if the boundary condition changes, and so when you train for any kind of machine learning models, when you want to guarantee the generalization, you really need to prepare a good set of training data. So if my task is to have a model that's able to predict the flow field for an unseen boundary conditions, I would definitely define a good distribution that sample boundary informations from this, and I will feed that into a ParameterNet. I will make the entire framework train well, such that it should
within the family of boundary conditions.
Yes.
So that's what you say, but you say it's adapting the solution, the mesh is within the training set, etc.
Maybe I should make it more clearly. This framework is meshless. There's no real mesh. It's only
it is equivalent to say a statement that is valid for any mesh. If it's
yes,
which is a strong statement. That's why I'm trying to maybe within the family of trained solutions that will fit with the data that you have.
Yes, I was more. Yeah.
Okay. Anyways, I will reach out later. I'll read the paper, and thank you very much. Thank you.
Okay, no problem. Thank you.
So we have a few more questions. Tim, do you want to go ahead? Tim, you're muted.
Sorry, no, I'm unmuted. How does time figure into this? Is it assumed that the flow field is constant over time, steady state, or is time an input somehow?
Yes, that's a good question. Time can be input to the parameter.
So it should be spatial and temporal coordinates input?
Spatial coordinates will only be put into ShapeNet. ShapeNet is only exclusive to spatial coordinates. Everything that's not spatial goes to ParameterNet.
Okay, and that works better than because like it's very standard for, well, not standard, but there are dynamic nerfs, for example, that put in T as another input into the, like where the spatial coordinates are instead of in the sort of ParameterNet. Does this work better? And do you think, might apply to other applications, if so?
Yes, for other application, I'm not sure, but from the viewpoint of reducer modeling of fluid systems, the only basically, if you think about the complexities of fluid systems, there are three types of complexities. First one is multi-scale, which corresponds to the spatial. Second one is parametric complexity, corresponds to bifurcation. Basically, it's bifurcation. And third one is on time, which corresponds to chaos. So these three monsters, the purpose of NIF is only to reduce the dimensionality on the first monster, which is the multi-scale, which corresponds to spatial degrees of freedom. That's why I only reduce the degree of freedom in the space. And that's sort of, because actually for fluid systems, that's actually the largest number of complexity comes from. It's the multi-scale. Think about if the world is just an ODE, let's say 10-dimensional ODE, I don't care how many parameters I have. I can run the ODE solver really, really fast. But if it's a 10 million or maybe 100 million ODE solvers, maybe just have one parameter, I have to run the simulation. It has to be really, really slow. So that's how the NIF architecture is developed to only tackle the spatial complexity. I'm going to come back to this after probably 5 minutes.
Okay, thank you.
Yeah, but this is a great question. You asked a great question ahead.
And we also have a question from Matt. Matt, do you want to go ahead and ask your question?
Am I audible?
Yes.
Okay. All right. So to summarize everybody's questions and your responses, the learning task here is to learn the ParameterNet, which takes all your boundary conditions and what time step we're at and anything else that's relevant. And it outputs the parameters of a function. And that function maps spatial coordinates to some field value like the density or temperature or whatever it is. Okay. So that there's presumably some modeling bias there. The ShapeNet has finite capacity. And presumably the output of your ParameterNet is smooth in the inputs. So whereas the kind of phenomena that you're modeling, as you just said, are very non-smooth. They have self-similarity at many scales. There are phase transitions in CFD phenomena. What kind, and so your modeling choices here are a bias for a particular kind of smoothness. Does this mean that when you zoom in on a tiny part of the field, that the function is smoother and smoother, or is it in some way recursive or fractal-like? How is this actually matched to the behavior of the phenomena that how is the function here matched to the behavior of the phenomena that you're trying to model?
This is a really deep question. About the bias, I haven't looked into, that basically goes back to trying to answer what's the bias of a hyper network. What's the kind of function bias of the hyper network? Does that give you, if you're given a limited number of information, and when it extract sort of, and I wouldn't say extrapolate, but let's say given the amount of, given a limited amount of information, and when it interpolates for some unseen data, how would this function be biased towards? So far, I would say I haven't really tried the case, try to, do some tasks like say super resolution. Maybe super resolution is a good task to see, because as actually really pressing really kind of feeding the network with low resolution information and really try to see how it gets the behavior, how it gets for high resolution inputs. I don't have answer to that,
but your claim is that this is a resolution independent representation. So
yes,
it's going to have some kind of variation as you change the scale at which you query it. Right? Otherwise, it's not resolution independent. So what is that behavior?
I don't know. I don't have answer to that. I haven't tested on the let's say task at super resolution to see how that works. Well, I would say more so sort of I'm not sure if I said resolution independent. Maybe I said what I said is discretization independent. That could be different things.
Okay. All right. I realize we're running way behind, so maybe I'll relinquish this question for a while.
Yeah, that's a good question. Yeah. Right. So this is kind of a task compared to the deep-neural net. As you can see, a deep-neural net with perhaps 60 times more parameters can't really reconstruct this simple signal because of the linear structure, as I just mentioned. Okay, so here I'm going to give some examples about how it actually can be used. So, for example, for an autoencoder for the mesh refinement, in these cases, I place sensors on the y-axis with 16, I think 16 sensors over there, and these 16 sensors basically are the input to the parameter, and it goes connected to a ShapeNet, and in the ShapeNet it takes two spatial inputs x and y, and it outputs, I believe here it's a temperature field for really tailored instability. So when you compare this kind of autoencoder task versus POD or CNN, you can see the Neural Implicit Flow performs the best because it's discretization independent. It does not care how you discretize the flow field. It has nothing to do with the mesh, no matter what kind of mesh it is. Yeah, but for other methods, you have to make some pixelization, which give you, which basically limits the best performance that you can get. Okay. And the second attack is a simple sort of data fit mesh-agnostic surrogate models. So basically, this is a problem of parametric one-dimensional model Shevchinski problem. So when you change the mu over there, you change the hyperviscosity over there, it can actually. So normally we know KS gives you a chaotic solution. But if you play around with viscosity, it actually can give you sometimes kind of oscillating waves, sometimes traveling waves. So in this case, we're not going to predict, the chaotic problem. We're going to test on sort of the bifurcation problem here. So and not chaotic, not really much chaotic over there. And we are given, I think it's 20. We give 20, 40, 60, I think simulations, 1D simulations, and we feed them into the ShapeNet. And the input to the ParameterNet is T and mu. The input to the ShapeNet is X, Y, no Z. Sorry about that. There's no Z. It's only X. Sorry, it's a 1D problem because. Okay, so we tested our previously someone asked a question about what if I just put a T and mu, put T and X, T and mu into just a simple, put them all into a simple feed-forward neural network and compared it with this Neural Implicit Flow. So how would that work? So as you can see on the bottom right over there, you see this MLP, the red line corresponds to that vanilla idea, the simple straightforward idea, and it gives you, when you're changing the number of training data, NIF gives you better generalizations. Okay, And if you fix the number of model parameters, you have fixed budget of the number of models parameter in your model, and you will see the NIF also performs generalized better than the previous sort of the vanilla simple idea. Just put X T mu into a single free-flowing network. Okay. So the next test is a mesh-agnostic DMD. So basically, I'm doing a little bit surgery to the neural protocol, basically asking the ParameterNet to only parameterize the last layer. So when I only parameterize the last layer, it has a very good physical meaning. And if the input to the ParameterNet is only just time t, because then if you go to write down the last layer expression for the last layer for the quantity of output with respect to the last layer, you will see the space and time is decoupled. Because the last layer is a linear, basically just a linear interactions between these two networks, and then you can extract the weights over there and plot them. So I have 10 weights over there. That basically means I have 10 different lines I can draw. So on the bottom left, you see 10 different colored lines over there. That's basically the latent representation. In this kind of modified NIF architecture, and you can extract this latent representation and just use it's a 10-dimensional. It's just a 10-dimensional time series, and you can apply a simple DMD on this data, and you can go back to the framework and you can actually get the DMD. You can apply DMD on any meshes. So I think this is probably the first time it can be done. Okay, so this problem is a flow of a cylinder. So as you can see, it has a good result match with our intuitions. Okay, so basically
we are going to have a question from Matt.
Yes. What is the question, Matt?
How do you make this invariant or equivariant to simple transformations? For example, moving the obstacle up and down in the field.
That's a great question. So far, it does not have any equivariant properties embedded in. Yeah, so far we haven't tried that approach yet.
So in some sense, it's a little more like memoization of the entire simulation.
Yes, in terms of the spatial, coordinate at least. So if you let's say if you translate this if you given, let's say, if you translate this flow, let's say changing the coordinate system just by translating it, maybe the x, y, just adding a constant, adding some offset constant over there. Then if you just evaluating the network on a new set of the offset locations, it will not work.
Mm-hmm. Okay.
Yeah. Okay. But for our purposes, it's sort of good enough. Okay, so the next text is compressing a 3D homogeneous isentropic turbulence with resolution above 2 million cells. So this task is very simple. I just want to see how can this be done? Can this be used to compressing a data set? So basically, I use this to train a 3D velocity field of this turbulence data set with 20 time steps. And this task is basically just throw this throw the data into the model, and I wanted to check, as at the end of this, the model just a bunch of parameters in the ParameterNet, right? So the network size compared to the original HDF5 data, we have basically 20 times smaller HDF5 data. And you can actually also compare it as a PDF. You can see it has good reconstructions. And if you compare the Q criterions, which involves higher order spatial derivatives, I would say it's more sort of a stringent comparisons. If you want to compare the multi-scale spatial field. So as you can see, it basically it almost, you can't really almost see, you can see some small difference, but not too much. Okay. The next text I would say perhaps a little bit more interesting is about predictive data-driven. So basically, it's using this is the text about sparse sensing. Okay, so you have imagine you are on the sea. You have 100 boats, and these boats can go anywhere and give you the temperature at that location. And now you want to collect those information on those 100 boats, the temperature information over there, and you want to reconstruct. You want to infer the global sea surface temperature. Okay, so there will be basically two questions. The first question is where to find the location of those 100 bolts should go. So basically the sensor location. What's the optimal sensor location? The second question is once you're getting those information from those optimal sensor locations, how are you going to use them to create to infer the global sea surface temperature? Okay, so the first question, we use traditional methods, basically POD kill time. Basically, it's just a pure decomposition of the data matrix over there, and you can the pivoting matrix give you the optimal sensor locations. That's traditional methods, and we use that. We use that, and we now we have the optimal sensor locations, and the sensor value of those optimal sensor locations goes to the input of our parameter net. And then the ShapeNet takes X, Y as input, no Z over there. And then we train this, we trained for 16 from 1990 to 2006 as our training data. And we predict the sea surface temperature for the next 16 years, basically up until 2022. Okay. So and it turns out that our framework generalized better than the traditional sort of POD kill down method, and the POD kill down basically just overfit after 5 sensors, which is kind of an interesting phenomena. It has been also validated in other papers. People also find out that the kill down, if you have more than 5 sensors, it can't really give you a better. It can't really give you a better generalization performance. But however, for our framework, once we hit after 400 sensors over there, where kill down basically overshoot to nowhere, I guess, we outperform the best performance from the we output the best performance from kill down over there. Okay, so the blue line corresponds to our performance. Okay, so here is basically a comparison against popular frameworks. So we test on a slice of a 3D. So basically it's a 2D turbulence data set, and we compared it against other popular frameworks like simple MLPs, Fourier neural network with different, the sigmas over there. You tuning this a little bit. We also compare with sirens, and we fix the number of network widths the same. So when you evaluate this spatial field, it will have the same computational complexity. So I think it's a fair comparison over there. And then we compared the model mean square error. As you can see, our model performed the best for 16 to 16 case, 36 case, and 75 cases as well. Our framework performed a little bit worse than the sirens for the 150 widths over there. Okay. And so next I want to talk about really more relevant to the audience is NIF on a little bit more realistic industry problems. So so first one I want to talk about is NIF for automotive aerodynamics, which is from my collaborator at the University of Michigan. So basically we have basically we have think about a geometry for a car. I think this work is funded by GM. We have 8-dimensional design parameters to design the shape of the car. It's 8-dimensional problems, and correspondingly we have you can generate in CFD simulations for many cases, and then we can use this. We can use NIF to perform a parametric surrogate modelings. As you can see, the mesh. So basically, the picture you see over there is correspond to the rear end of the car. As you can see, some places the mesh size is really small, And you can think about if you use a convolutional neural network, you probably your pixelization has to be really, really fine. Otherwise, you were missing those tiny little details on the car. Okay. And wait a minute. Yes, and basically the DVHNet basically it's another way of calling the NIF for architecture. Okay, the next problem I wanted to show is basically NIF. I think it's recently been published, also from the collaborator at the University of Michigan. Is for use NIF for shape optimization in gas turbine machines. So this work I think is funded by Raytheon Technologies. So as you can see, so in this case, if I remember correctly, we have 4 parameters to tune the airfoil inside the compressor. As you can see, the quantity of interest, contains density, pressure, velocity, and stagnation densities as well. It contains everything that a CFD solver would produce. And then, as you can see, there's also some lambda shock waves inside these. It's a complex flow phenomena inside these compressors. Okay, and you see, I think this is a plot. So the task is to perform shape optimizations, and as you can see, the emulation-based DO, basically we use NIF as a surrogate model to perform a Bayesian optimization. As you can see, the cost for perform the basically using a surrogate-based optimization is really fast compared to if you use a CFD. If you use a CFD solver coupled with a Bayesian optimization to perform the shape optimization.
May I ask a question here? What is the cost objective that you're optimizing for?
Let me see. I can't really give you right now the, but I can probably give you the paper that you refers to.
Because I guess the other question I had in mind is if the cost objective is a quantity that's associated with the shape of the airfoil itself. Let's say it's a drag that you have to compute along the whatever the predicted optimal shape is. Then over the course of the optimization, how do you then handle the fact that this boundary is at an unknown location? Since the NIF framework itself does not really have a notion of specific nodes in space.
What do you mean by specific nodes in space?
Well, let's say that you want to minimize drag over the airfoil. So you have to integrate along a certain path in space,
yes.
The tangential stress. But that path itself depends on the parameter values that parameterize your geometry, right? And so how would you account for this, I guess, geometry dependence of computing the objective function itself in this framework? But yeah, I can also just check out the paper if you don't have the answer on the top of your mind.
Yes, so I can actually read a kind of comparative paper from George. So basically, he's using, I think he just published last week. He's using DeepNet to optimize the drag, if I remember correctly, and he computes. So basically, for a new parameter operating conditions, you can give an entire CFD field, right? But you also know you can also figure out the geometry. You can also figure out exactly where the geometry boundary is. So you can use, but and at the same time you have the geometry coordinates, and you have the entire field. You can query any pressure values or drag value at those points, and then you can I think what George did is he used Green's function to compute the surface integrals, and then basically use that as it goes back to the Bayesian optimization to as output of this black box surrogate model to the Bayesian optimization module. Then the Bayesian optimization module determines where to sample the next parameters.
I see. Okay,
Okay.
yeah, we can talk about that afterwards.
Yeah.
So, thank you.
No problem. Okay. The next one is sort of an ongoing. It's demonstration on using NIF for a 3D RANS problem. It's on a transonic wing. It's a ONR M6 problem. Basically, it's a standard tutorial problem in SU2. So we have the three input parameters: angle of attack, Reynolds number, and Mach number. And as you can see, this is on the left. This is isocontrol for the Mach number and the pressure coefficient. Over there, we're currently still trying to develop a framework instead of just a surrogate model, but trying to develop a hybrid framework to accelerate the CFD simulations, actually parametric CFD simulations. Okay, so this is sort of an ongoing work. Okay, so next one I want to talk about just how can I use NIF and scale. I have prepared a NIF a package for you together with a bunch of Google Colabs tutorials. And currently the backend is in TensorFlow too, but PyTorch version will become online soon. I guess I'll probably switch to migrate to PyTorch entirely, kind of abandon TensorFlow. But there's something I have prepared. If you want to give it a try, if you want to, it can also handles. Also implement a lot of things, digging into the TensorFlow to make it a scale. And you can also get in the derivatives easily, input-output derivatives, and it can also handle multi-scale data. And you can also, if you want to play around with some regularizations, it's also possible. Okay. That's it. So as a summary, NIF-based frameworks outperform the state-of-the-art methods in terms of data fit, mesh-agnostic models, data-driven sparse sensing, and learning latent representation of high-dimensional data from arbitrary complex mesh structure without unnecessary loss. So the NIF, the key idea of NIF is isolating spatial complexity, basically the multi-scale, away from the temporal and parametric velocity, which is the chaos and bifurcations. And we're only performing the dimensionality reduction in space. Okay, because that's actually kind of goes along with the traditional line of low-dimensional manifold methods. So if you look at the figure on the right over there, starting from the 1960s issues, the POD, the Gallatin, Worm, Koopman, LSPG, data-driven closure, or the CNN, P-ROMs, they're all based on the concept of low-dimensional manifold. And that low-dimensional manifold is only reducing the complexity of the space. On the other end, there will be methods embedding invariance. For example, if you're using graph neural network architectures, and if you're using, if we go back to early days, maybe it's can say it's starting from the PDNet in 2018, ICML. That's the on another direction. On the right bottom, you see using physics-informed neural network, basically along the line of George Kardidakis. We are sort of in between this low-dimensional manifold and the physics form, but our purpose is to leverage those tools to help us to on the direction of basically the philosophy of using low-dimensional manifold for reduced models. Okay. And if you can look at the paper right now, it's published on JMLR. The link, the title to the paper is over there on the bottom. And I want to also thank you. Thank you for your attending my talk today, and I'm happy to take more questions if we still got time. Right.
Thank you very much for the super interesting talk. We still have a little bit of time for questions. I see that Matt has one, so Matt, you can go ahead. Please.
Okay, intriguing talk, and I suspected you were going to head over towards shape optimization, using these to reduce the time it takes for the simulation step. Are these all adjoint method optimizations that you're presenting?
Oh, the method I'm presenting is not adjoint optimization. It's using a global optimization technique called a Bayesian optimization. It does not use any information of derivative.
Okay. So generally when using in function approximation, to use a proxy function to speed up an optimization, you also have to figure in the time it takes and the data it takes to estimate that function in the first place. So are you at the point where it's an overall win yet?
I believe in this case it's overall win, but I would say if we want to make it better, we can basically I'm currently pursuing on this line because that line sort of my PhD advisor's line. I'm pursuing a new line, basically developing a hybrid framework to accelerate CFD simulations. So even if for the overhead it can be accelerated. Even for the overhead, maybe you don't have to run 200 simulations. Maybe you run, let's say, 10 simulations, and you can build up a surrogate model based on NIF and use that model to accelerate the rest, 190 simulations.
And apropos what the direction you're taking now, do you have some protocol for validating the NIF against actual physical equations?
You mean
where is the approximation reliable? Where in your parameter spaces can you depend on the NIF?
I would say so far, if you're patient enough, and if your solver is robust, basically I'm using NIF to give an initial guess for the CFD simulations for unseen parameter operating conditions. And if your CFD solver is robust enough, it should first it should converge to machine precision. And if the NIF is giving you a reasonable predictions, it should also accelerate should be accelerating the convergence of the solution, especially for the larger scale part. So for most numerical solvers, it's very good at reducing the error, high frequency error. But for neural networks, it's good at approximating a larger scale. So you can combine them together to reducing. Yeah.
Makes sense.
Yes.
Thanks.
Are there any other questions? Mohsin, go ahead.
Just a quick question, maybe two, quickly. So because you have this slide up and you have Reynolds number there, so if you switch regimes by changing the Reynolds number, you are expecting this model to follow, or will be valid only within a regime?
It can be only work on within a regime, within the training regime.
Within a regime, you can switch between turbulent and laminar. And the last question is, when you did estimation using sensors like sparse sensing, I saw the QDime diverging. So I am wondering, is it because of the QDime POD, or is it because you didn't close? So how did you do with the QDime? Did you find the optimal sensor position and then you use a ROM observer, or how did you estimate?
Yes. So basically, the QDime algorithm it gives you the optimal sensor location. At the same time, it also gives you how to mapping from the sensor values to the full field. It's basically a linear problem. It's a least square problem.
I see.
Yeah.
Because that curve going up means that you have a closure term that is missing. If you close the model and then you observe, it should be stable. So I'm suspecting it's not because of POD. You have the ROM and you need to close to add a closure.
There's no ROM here. There's no projection-based ROM. There's no dynamical system here. It's a very simple least square problem, static.
Okay. So maybe, yeah. I mean, to compare fairly, you should maybe add dynamics in the other methods.
I mean, this task is a static task. There's no, even for the benchmark, there's no dynamics. There's no dynamics involved.
So you're just learning a map from sensor measurements to temperature fields at a given time,
yes.
right?
Yeah.
Yes, exactly. That's the same case that being used in Criticast paper, also from University of Washington, when they.
Yeah. No, I'm just saying, if we do estimation, we usually have, if we have the luxury to have QDIME, POD, best POD mode, then we push it to have a ROM and closure and observer. That's how we will compare to the best state-of-the-art estimation. Not
yes, yes,
yeah, maybe,
yes,
I don't know. Just observation. That's not.
Yeah, I agree. But what kind of governing equation you want to use here? You want to use for the sea surface temperature? I don't know what's the proper governing equation to use here.
I see.
Yeah.
Okay. Thank you.
It's a bit too complicated to use that equation. Yeah.
All right. Thanks. Thank you.
So I also had a question. So the comparison you mentioned with DeepNet was interesting because it shows that NIF can also be interpreted as operator learning framework.
Yes.
In addition to reduced order modeling. And so there's a lot of interest right now in trying to integrate physics into the learning of these operator learning approaches.
Yes.
Have you thought of doing something similar with NIF?
Yes, but I didn't have enough bandwidth to actually do that. But I know that Google actually has a paper kind of similar going on this line. So they are basically, they call it hyper-pin framework. And they show that the framework can outperform the classical pin in terms of using a smaller network to achieve the same performance. But I have personally, I feels like using. I would probably use NIF more like sort of a surrogate model and use it instead of trying to sort of you're making the loss function fancier using a bunch of PDEs because I feels you could you are able to do. I'm not sure, but I feel like that line is probably already being explored extensively by George. So I'm just trying to avoid going to collide with him.
Yeah. Anyone else has questions? So maybe another one for me in the meantime. So in your ParameterNet, if I understand well, you have a bunch of nonlinear layers from parameter to the latent representation. And then from the latent representation to the weights of the ShapeNet, you only have a linear matrix.
One layer, yes.
So what is the motivation for having all the nonlinearity before the latent space and none after that, as opposed to some before, some after, or all of it after? Was there a reason behind that?
Yeah. So the reason is probably the fear of creating a super large neural network. So if you think about the ShapeNet, let's say ShapeNet has maybe the ShapeNet size of the ShapeNet for a complicated problem could be 10,000 widths. 10,000 in total. There's 10,000 weights and bias in the ShapeNet, and you imagine you're mapping from 3 to 10,000, and I would say if a linear mapping works, that would be great. If you want to use complicated nonlinear mappings, let's say 3 to it does not make sense to mapping from 3 to 1 or 3 to 2, right? You probably want to mapping from 3 to 100, then 100 to 10,000. But 100 to 10,000, it's a really, really troublesome matrix multiplications for your computer to run. It's going to be really memory consuming, especially from the GPU perspective. So I'm trying to make the mapping from latent representation to the weights and bias as simple as possible. That's basically that's mostly from the computational perspective. And if you want, you can also interpret this this way. So basically, the ParameterNet takes parameter informations, and it produces some sort of principal component coefficient. And for the principal component coefficient, the vector is basically represented by the matrix 3 to 10,000. So effectively, you can say, I'm learning a linear latent representation inside the weights and bias of ShapeNet, which corresponds to optimally describe, optimally describe the spatial-temporal field.
And those coefficients themselves depend non-linearly on the parameters. So that might not be too big of a limitation. I see. Oh, so there's someone asking a question in the chat. I'll just ask for that person whose mic is not working. So he says, do you know how robust is the ParameterNet to noisy sensor observations, especially if there is some domain shift between train and inference, like calibration errors?
That's a great question. So I guess part of the question, well, George already gave me a good guess for this type of framework. So George, he did a fair comparison with between NIF and a neural operator, and he's sorry, not NIF, DeepNet, DeepNet and neural operator, and he found that DeepNet is more robust to the noisy observations compared to NIF. I'm sorry, compared to neural operator, so I think because the framework is sort of a nonlinear generalization of George's framework, I assume my framework should have similar benefits over if let's say a comparator neural operator.